more kinematics, but now we're moving into 2 dimensions, which might sound intense or maybe not, but what it is basically everything you've been doing, you do it twice. So you just like, it's just like twice as many steps, but it's the same sort of process that we've been doing. You're still going to want to identify variables, figure out equations that make sense, but now you just write out 2 lists of everything, one in the x and one in the y, because the answer to that last question is they're independent. The motion in the x, the motion in the y, independent. So you don't have to worry about, x is y squared, or like anything like that. They're completely independent. What links them together is the time variable. And so that allows you to maybe, like, if you're missing 2 variables in the y coordinate, system part, then, you can get some information from the x and then plug it in as one of your variables in the y, maybe how long it's been in the air or something like that. So we still have to, worry about things like displacement and average velocity, but now our displacement, right, which you've seen this before, like it's the delta r, we saw like delta x, change in position, it's still, instead of being just in 1 dimension, now we have 2 dimensions. So all this adding and subtracting of vectors is going to become more important now, because now we're worried about vector things, right? I mean, technically they were vectors before, but it was just like, 5 I hat, right? Like 5 meters I hat or something like that. So now it's going to have some x component and maybe some y component. So we still can think about things like average velocity. So this is sort of very, very similar to 1 dimension. It's the change in position, right? The displacement over your change in time, right? That little delta means change in, so it's final minus initial. And so we have an r instead of an x. And so here could be your trajectory. Here's x versus y. So this could be your position over time, right? So you could have a vector that describes your displacement, right? So it's not necessarily in x or in y, but it's a vector that has x and y components that you could find. And then also your velocities will have, could have x and y components if you're not traveling along just one axis. So let's get a little bit of practice in. I know you guys did the quiz, which had some vectors in it. Let's do a little vector practice now related to position. So we have a dragonfly that's initially observed at a position that is 2 meters I hat plus 3.5 meters j hat. And then 3 seconds later, it's at this new position, r final, or r sub f. And it's minus 3 meters I hat plus 5.5 meters j hat. And I want to know, what is the dragonfly's displacement at t equals 3 seconds? It's a real struggle to do that now. You did it much faster. So you might be able to do this in your head, but I don't know about you, but I don't always trust my head. So I would write it down, just because if I write it down, at least I can see where I went wrong. If I get something that's surprising later. So, I've seen a lot of the same answer. So if you got maybe something like number 3, what were you thinking? How did you do this? Either in your head or I'll write it down. Draw some coordinate points? Okay, so I'll need a coordinate system, right? Okay, and then the first one is at 2 and then 3.5. 2, 1, 2, 3.5. Okay, and the other one is minus 3, 5.5. Okay.
And then because the answers are in the components, so you can just see how much it moved from each.
Right, so we have these already written out, so our final is minus 3I hat plus 5.5. J hat, these are meters. And then our initial is 2I hat in meters. And 3.5 meters in J hat. So then, since they're nice and in components, we can just do, oh, let's see, we have to do R final minus R initial. So we have to subtract, subtract, subtract. And it becomes minus 5 meters in the I hat plus 2 meters in the J hat. Is that what I got up there? Yes. Good. Excellent. Consistency is key. Okay, so we could get that. Now, if we were to draw this in the picture, how would I draw his displacement vector? It's the sum of two of the, right, it's the difference of the vectors, which is the sum of when you turn one negative, right? So how would I draw in this picture what it looks like? You gotta move one of the vectors. Good, which one do you want to move?
Short.
The short one. We'll move the initial. Okay, so how do I move it? Shift it up.
To the, like the tail.
Oh, up here?
Mm-hmm.
Something like this.
And you connect the,
And then I connect it like this. Does anyone think differently?
I don't know.
Well, you're subtracting them.
You're subtracting, so you missed a step. You got to flip it first,
Oh.
right? So it's adding as long as you make it. So since we're doing final minus initial, it's adding as long as you do our final plus a negative of this one, right? So we have to flip it first before we can add it. But other than that, yes. So we have to flip this first so it goes like this. Oh, it's already connected the way we want it, right? Right, so we just flipped it this way, and it's connected to that. So that might not always happen to you, but it worked out really well that I don't have to draw it again. So it's already connected tip to tail, the way that I drew it. So now all I have to do is do the resultant, like you were saying, tail to tail, tip to tip. And then this vector, how big is this vector? So we could check. Is it minus 5 plus 2? So 1, 2, 3, 4, 5. Good. And then is it plus 2? Oof. Where is this? Oh, this is in the half. Because I was like, this is not on this one or this one. Okay, so it's half. And then here's 1, 2. Yeah, that looks good. So both of the answers should agree. So if I'm asking for one of these pieces somewhere, you could always double check. If I'm just asking for the components, you could draw a little picture for yourself. If I'm asking for the picture, you could write out the components just to check that everything makes sense. It should all work out to agree.
So you can always just flip one of those to make it tip to tail.
Well, so
So
if you're doing a subtraction, you have to flip the one that is being subtracted in order, right? So you have to do, in order to draw them as added, right, you have to make this happen. So you have to make one of them negative, right? So instead of R final minus initial, I'm doing R final plus minus of this, right? So I can add them. Whenever you have a minus of a vector, you have to flip it, no matter where it is. So if I was doing, if I had them nice and lined up like this, and I wanted to, somehow subtract them, right? I still have to do this, even though that means I have to move it. So whenever you have a negative vector, you have to flip it on your picture. Good question. Any other questions on this? Okay, so the next question is, and I should have left what I wrote, but I will write it down again. Next question is, what's the unit vector pointed along the direction of the dragonfly's displacement? And so here's the displacement vector. What's the unit vector? Couple answers, and they seem to be the same, which is good. So if you're getting it, you're at least all getting it the same. That's what I got. So if you're stuck, unit vectors can be kind of tricky, and like explaining them can be like, just give me a few tries, you know, like we will get there, right? So if you've already been hit by the unit vector knowledge, like good. The rest of you, I will get you, right? We will understand these. They can be really tricky. So I drew here again our displacement vector. So this is the same vector that I drew when we added that negative one, right? But I just slid it so that it's at the origin. It's the same vector because I haven't twisted it or stretched it or squished it. It's the same vector. So this is -5 plus 2, right? It was up here before, but it's the same vector. This is our displacement vector. So I drew it here to talk about what the unit vector is. So a unit vector has the same direction as the original vector, but a magnitude of 1. So this one is 5 and then 2. This has a magnitude that is larger than 1. Agreed? So I want a little vector that has the same direction, but a magnitude of 1. Now the operation that gives you that stretching or squishing of a vector without changing the direction is what? Not the theorem. What operation takes a vector and doesn't change the direction, but it stretches it or squishes it? Multiplication by a scalar. Any scalar, right? So I remember like way back to like the second day that we were together, I think there was like a picture where it was like A, and then this would be like 2A, and then 3A would look like this. So multiplying a vector by a scalar just stretches it. Or if it's smaller, like this could be 1/2 A. So it's just changing the length, but it doesn't change the direction, which is exactly what we want. Scalar multiplication. And we want to shrink this vector without changing the direction so that the magnitude is 1. Right? So we want to take this delta R and we want to multiply it by something so that it has the same direction but a magnitude of 1. And so what you guys, I think I heard coming out, is that this scalar, okay, it has to be smaller than 1, right? We want it to be smaller, right? So we don't want to multiply by like 5. That's just going to make it bigger. We want to multiply by 1/5 or something like that. And so what we multiply it by is 1 over its magnitude. So this is the scalar that we multiply delta R by, is 1 over its magnitude. And so what that does is it takes that big vector and it divides it by the length of itself, and you just get 1. But you keep the same direction, which is important. Because that's the information we want in the unit vector, right? So magnitude of 1, direction is the same as the original vector. So what this ends up, when you're actually computing what it is, so we have, our delta R, we could write that in, 5 meters I hat plus 2 meters J hat. We could write it like this. And then we could, we can distribute this across the two pieces, right? Because, so we could divide the magnitude in both of these pieces. So then the magnitude is the Pythagorean theorem. That's where that comes in. So in order to find the magnitude of this, right, the length of this vector, we know that this edge is 5 down here. this edge is 2 up here, and so this hypotenuse is, so the magnitude of r, the hypotenuse is the square root of 2 squared plus 5 squared. 4 plus 25, 29, square root of 29. So if you take 5 divided by square root of 29, and 2 divided by square root of 29, should get, yes?
I'm just wondering, like, what's the benefit of knowing your unit vector?
Oh, good. So they might seem really annoying right now, but later on, we're going to have, so more complicated formulas where you do all this multiplication of stuff, and then it's still, so in order to find your vector, the magnitude is really complicated to find, but then the direction is just the same as your displacement vector, right? So like you could say in order to find the force, I have to do all these different things to figure out what the magnitude of the force is. But then the direction of the force, you could just find out with your unit vector, the direction, and it has no units to it, so then you just take your magnitude, the new complicated magnitude, multiply it by that little r hat, and you have your vector. So it makes it very easy once you get to the next step where you have something in the same direction as something, but its magnitude is really complicated. So then you can just take that crazy magnitude, multiply it by this little unit vector, and you have, right? So now once you have a vector of unit 1, you can multiply by anything, any units, any size. It's not whatever you like. Good question, though. Any other questions? Unit vectors? Kind of weird at first, but they're very, very helpful. Yes, and so if you Pythagorean theorem this thing, it should give you 1 as the magnitude.
Yeah.
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 Some of them don't, I don't think. But these are 1 over square root of 2, I think. So those should work, but not all of them. All right, so my next question is talking about the same vector. I want to know, what is the direction of the dragonfly's displacement described by an angle relative to the positive x-axis? You're just a process of elimination? There.
If we can actually know.
What if I'm wrong? What if it's 5? What if the answer is not up there? Double check my work. But yes, process of elimination is good too. If you're kind of stuck, go back to the way you do your homework, right? Draw a picture.
How are your tests structured? Like multiple choice, some short answers? We all short answers.
I do a little bit of short answer, like those quick questions that I have posted. And so like I mentioned, I will pull at least 1 directly from the slides. It may be something we didn't cover in class, but it will be on the slides that you can look at, and I will post. So there'll be probably 5-ish multiple choice. And then I will do problems kind of like a homework problem. It might be like a little bit longer than that, like maybe a couple parts to it. And then probably, like 5 of those. So it'll take you longer to do the show your work, but then you can get like more partial credit. I try to give partial credit on multiple choice too if you like show something that like makes sense. That might give you a point or 2, right? So I try to give, I give partial credit. Well, multiple choice is hard, but I have given it in the past. If you can like say why it's not something, or, I won't show it. Unless I could even be wrong, so even if I show the answer, it could be wrong. Are there any questions on what CW or CCW means?
Clockwise, counterclockwise.
Clockwise, counterclockwise.
Just
Yes.
out of it. I'm staring. That's the only thing I was staring at.
Yeah, that one I usually forget to say. But yeah, clockwise.
Okay. Marty's ready.
Marty is ready.
She did the whole thing.
So if I reveal it.
Yeah.
Did you draw the picture? Is there a picture in front of you?
I drew a clock.
You drew a clock? Fair. I always have to sit there and be like, which way is clockwise? You know,
I drew
they're
a
like,
picture. You can just
okay,
look at the
it's
clock.
like this, right?
I drew a
was
very
like, wait a
nice
second.
picture.
Yeah.
Very short.
Like everyone's gonna be like looking at the clock, being like, okay. It goes this way. I always like, so it's weird, but like counterclockwise is the way that you normally define angles. I don't know if that helps you. If you've like been in a lot of math classes and they talk about like positive angles or like define like this, I don't know. So, but it's kind of, yeah. Anyway, however you remember, you might just think about what a clock looks like.
Ka and caca.
Caw and caw, yes. So this picture, you know, you could draw a picture like this, and then what I'm asking for, how do I draw the angle that I'm asking for here?
Relative to the x-axis.
You just draw it between. You're asking for the angle from right there going to the positive x-axis.
So this one.
So that angle, yeah.
Right, so some people were able to process of elimination. It can't be 21 degrees, right? That's little, right? And then if you go less than 180 down here, you're in the negative y range. So you can kind of process of elimination from there. Yes. Okay, so now we have a question about the average velocity over this time interval. Notice I already have a little r hat here. So I took, so that's the direction, right?
So it's in the x direction. Oh, no, it's just in
It's in the r hat direction,
oh,
right?
that.
I haven't did it.
I haven't. Let's change it.
So if you're a little stuck, try to write down, if you have your picture already, try to write down any variables I've given you. And what you're looking for equals question mark.
How do you find the sign?
Thanks. I got that part, yeah.
That's the same. Would you make one?
So I don't, when I was doing GC calculate, so I did too.
Can we just put an angle on her?
Good questions. Very good questions. Okay, tell me a little bit about what were you thinking? What variables do we have that can help you solve the problem, and what are we looking for?
We have our magnitude of our r.
We have the magnitude of r,
For r.
the delta r, right?
Right.
Right. So this, what variable is this?
This is your r vector length.
Right. Okay. So this is, you know, so we could say this is
Delta x or delta
right.
r.
That looks so redundant. Like the magnitude of delta r is the magnitude of delta r. But
Hey, that's
is that confusing? Okay. Well, okay. So it's kind of like delta x, right?
right.
So like I'll just put parentheses. This is our delta x. Right. If you're thinking about like delta x equation of love, stuff like that, right? All right. You know, I'll just write it as delta x, but just know that it's r, right? So, right? Sorry if that's confusing. All right, so, all right, what else do we have?
We have time.
We have time. Very good. We have a delta time. I'll write a delta time. 3 seconds. Okay. And what is the magnitude of r?
5.38.
5.38 meters. Meters. Okay. And then what am I looking for? The velocity. The average velocity. Yes.
Yes.
So now, hopefully, this is triggering something inside of you about an equation. Are you triggered?
We're triggered.
You're triggered? What is it?
I think it's negative 1.8 because of where it's going.
The equation. Sorry, you're jumping ahead of me. You're too fast for me. Too
Delta
fast.
X over delta T.
Okay, the average, right, equals delta x or delta r, right? So this could be, you know, delta x, we'll do delta x. This is the way I wrote it. Kind of weird, but this is just kind of linking you in, right?
Yeah.
Okay, so this is the equation we're going to use.
Oh my gosh, those are the two variables we have.
These are the two variables that you have.
Oh my god.
Very good. So then you can figure figure out the magnitude, right, of the average, right? Magnitude, not so bad. Right, you just divide one by the other.
What's the
What's the
direction?
direction?
What's the direction?
Our
Our hat. Very good.
Right, but I mean, like, how, your sign, so it's just positive, it's just always positive?
No, I think it's negative. No.
Was it positive or negative?
That's what I'm saying, like, what's the,
What does
doesn't the
it
sign,
mean?
doesn't the sign tell you direction? If it's
The sign tells you direction.
Velocity, if it's negative, it's going in a negative direction. So like, how do you know which direction you're going in? Because
Right.
you're not,
Well, you have to think about where your vector is.
right, but you're not just along the x and y axis, you're moving.
Right.
But it's all on a coordinate.
in line.
Okay, so what would it mean if we had, what would it mean if we had negative this unit vector? How would I draw that?
Oh, then it would be going like.
Did it would look like this, right? And we could slide this, you know,
Right.
anywhere, right? So if the velocity is negative, that just means it's flipping,
It's not.
right? So it's not, right? Because our dragonfly is going from, you know, a point down here, right, to a point up here. So its velocity is along the positive r hat, right? It's along the positive r hat. Because r hat has negative components to it, that's fine. But the dragonfly, of the way we've defined r hat, right, it's going along the positive r hat. Because you'll notice this has a positive y component and a negative x component. So is it positive? Is it negative? Right? So that's confusing. So you want to worry about just how did you define your, you know, your positive r hat, and we're just going along that direction. So this is where I'm saying that the unit vector makes it easier when you move on. It kind of keeps track of direction for you. Okay, so similarly, instantaneous velocity, just like in one dimension, it talks about the velocity at a certain moment in time. So you could think about if you have some picture, right, of here's your position versus time, right? So you had, you know, you could have like any sort of plot, right? And so the average velocity could, you know, be the slope of this line, right? If you connect the endpoints, that would be the average velocity. But your instantaneous velocity could be different from that. So it's the velocity at a certain little instance of time. So you can think about smaller and smaller intervals, and you shrink down to a tiny little interval just around that time, and that would be your instantaneous velocity. So it could be different. So you could have, you know, between 1 and 2 seconds, you have a velocity of 30 meters per second. But between time equals 2 seconds and 3 seconds, you have 40 meters per second. Your average velocity would be 35 meters per second, right? But your instantaneous velocity can be different than the average. Right, but same idea as in one dimension. And the magnitude of your velocity is still the speed. We'll skip this, you can play along at home. Acceleration, again, same game. Now, average acceleration is the change in velocity over change in time. Velocity is a vector now, instead of just a, you know, not a scalar or one-dimensional vector sort of thing. The same thing as we did for average velocity, right? So you can figure out the magnitude, right? Figure out what variables you have, figure out the magnitude, and you can use your little r hat to keep track of direction. And here are the equations of motion that you are familiar with, right? So this one, right, if we subtract over x initial, the x naught, this is our what equation? Delta x equation of love. Below it is the delta y equation of love. Still works when you use y. Velocity, yep, so this is both hat, right? X flavor, y flavor. This is the Cadillac, X flavor, Y flavor. So since these variables are independent, right, we've done where, you know, X is in this direction, right? And we've done where X is in this direction. And it's the same thing. It's not just where, you know, X is now Y, right? But same sort of process. It's just now we have these equations.